When industrial coatings undergo severe environmental stress, failure is catastrophic. The surface layer buckles and cracks, suddenly spalling away from the substrate in jagged flakes. To solve this, we must distinguish between two independent mechanical properties. The first is cohesion, which refers to the internal structural integrity of the coating material itself. The second is adhesion, the specific bond strength located at the microscopic interface where the coating meets the substrate. When a field failure occurs, the root cause is often visually ambiguous. The fracture line frequently weaves through both the top layer and the boundary interface, making it impossible to determine whether the weakness was cohesive or adhesive simply by looking at the damage. Without a standardized testing architecture, engineers cannot isolate these precise failure mechanisms. This lack of data prevents the targeted refinements necessary to improve the performance of the material system. Accurate quantification requires a specific alignment, matching the test methodology to the material properties, the expected field loads, and the substrate's geometry. This is a testing decision matrix, the framework material scientists use to categorize evaluation methods. It divides the taxonomy of adhesion testing into three distinct branches based on the nature of the applied force. The first branch contains normal force methods. These evaluate bond strength by pulling the materials apart perfectly perpendicular to the interface. The second branch covers shear and lateral methods. These evaluate integrity through forces applied parallel to the surface, such as scraping, scratching, or cutting. The third branch represents advanced energy-based methods. These do not just measure a mechanical breaking point, they calculate the thermodynamic fracture energy required to cause debonding. This matrix serves as the operational blueprint for our analysis, guiding the transition from basic standardized pulling to complex, multi-factor accelerated testing. Perpendicular stress testing is most commonly executed through the standard cylindrical tensile test. Standards like ASTM C633-13 or GHOST 9.304-87 define the protocols for these tests, which are widely used to evaluate Verneuil sprayed coatings. The physical setup involves bonding a rigid pull tab directly to the surface of the coating, creating a mechanical interface for extraction. As the tab is pulled away from the substrate, we apply a stress map overlay. This represents a finite element method, or FEM, analysis, a computational tool used to predict how materials react to physical forces. The FEM reveals a major vulnerability: premature stress concentrations at the sharp edges of the specimen. These spikes in force can cause the coating to fail at the perimeter before the true maximum adhesion strength is reached in the center. Therefore, conducting an FEM stress-strain analysis is a strict prerequisite. It allows engineers to verify that the stress is uniform across the entire interface before the physical test begins. By optimizing the cylindrical specimen geometry, such as rounding or beveling the edges, engineers can mitigate these concentrations, ensuring the measurement accuracy reflects the actual bond strength. In practice, pull-off tests on primer coatings for steel show how this data scales. Depending on the thickness of the primer, these tests successfully isolate adhesion strengths ranging from 2.5 to 5 megapascals. A megapascal, or MPa, is a standard unit used to measure internal pressure and tensile strength. However, advanced materials like environmental barrier coatings, or EDCs, present unique challenges. EBCs are protective layers used to shield silicon carbide composites, known as SiC substrates, from high-temperature degradation. In these systems, the adhesive used to bond the pull tab introduces a hidden variable, thermoelastic residual stresses. These internal stresses can weaken the coating before the test even starts, skewing the final results. To maintain the validity of a normal force test, the specimen architecture must be engineered to neutralize these external thermal stresses, ensuring the result represents pure, uniform perpendicular force. When perpendicular force is not the primary load, engineers shift to lateral shear methodologies, beginning with the standardized crosscut test. According to the ISO 2409 standard, a multi-blade tool is used to score a uniform grid pattern entirely through the coating to the underlying substrate, typically aluminum or a polymer. The spacing of this grid is not a choice. It is dictated by the specific thickness of the coating and the relative hardness of the substrate beneath it. Evaluation is based on a classification scale from 0 to 1. Engineers measure the percentage of flaking that occurs at the intersections of the grid to determine the final adhesion grade. For more robust systems like chromium nitride coatings on steel, engineers employ scratch testing. In this test, a specialized stylus applies either a constant or a progressively increasing load while being dragged laterally across the surface. This progressive force methodically forces failures, allowing us to identify the exact cohesion limits of the material and the specific sites where interfacial adhesion gives way. However, the data from a mechanical scratch test is fundamentally incomplete without secondary verification. Engineers follow the scratch with scanning electron microscopy, or SEM. SEM uses electron beams to create high-resolution images, detecting microscopic delaminations and cracks at the interface that visual inspection would miss. Together, these lateral methodologies spatially map exactly where internal cohesive strength fails and localized interfacial peeling begins. The most sophisticated tests move away from measuring raw mechanical failure loads toward advanced fracture mechanics, the calculation of required energy. The primary tool for this is the blister test, which initiates a controlled active debonding process. Pressurized fluid or gas is injected into the interface through a microscopic hole in the substrate. This forces the coating to bow upward, forming a symmetrical dome or blister. We then add a metrology layer called digital image correlation, or DIC. DIC is an optical, non-contact method that tracks surface changes in real time to calculate strain. As the blister expands, DIC provides high-resolution tracking of the deformation and strain fields across the surface of the coating. This raw optical data is fed into an FEM computational model, which integrates the visual strain mapping with numerical stress analysis. The final analytical output of this combined system is a measurement known as normalized energy. Normalized energy is the quantification of the thermodynamic work required to initiate the first crack and propagate the debonding wave across the interface. By focusing on energy rather than raw force, engineers can mathematically account for variables like prior surface treatments or active state corrosion that would otherwise skew the data. This integration of optical metrology and computational modeling elevates adhesion testing from a simple mechanical break into a precise, predictive thermodynamic measurement. Ultimately, all of these methodologies serve one function. They validate the microscopic surface preparation that occurred before the coating was applied. For example, abrasive blast cleaning increases surface area to promote mechanical interlocking. Data from pull-off and tape X-cut tests consistently show that these jagged surface profiles yield the highest adhesion scores. Chemical preparations work similarly. Strong acid etching alters the micro-shear strength properties at the boundary, optimizing the adhesion between a resin and a titanium substrate. Engineers use Pearson correlation analysis to prove this relationship mathematically. A Pearson correlation is a statistical measure of how closely two variables move together. In this case, it shows a direct link between concrete substrate roughness and ultimate pull-off adhesion strength. Surface preparation techniques and the specific standardized tests used to measure them are inextricably linked variables in the equation of interface integrity. This returns us to our testing decision matrix. Each branch offers a specific analytical path. We isolate perpendicular force for thermal sprays, utilize lateral shear to map flaking in polymers, and deploy energy models for complex environmental barriers. Mismatching the test to the material system leads to false positives and undetected cohesive flaws, which eventually result in failure in the field. Mastering the standard specifications from ASTM, ISO, and GOST is just as critical as the formulation of the coating itself. In modern material science, proper test architecture is the only definitive mechanism to mathematically model, quantify, and guarantee true interfacial bond strength.